Natural physics is a concept astrophysicist LeRoy developed that explains in down-to-earth scenarios how the principles of physics could have come about from observing nature. Each episode begins with a scenario, followed by an example to illustrate the application of these principles in futuristic research at the frontiers of science, such as LeRoy's astrophysics doctoral research, and then concludes with an exploration of how these same principles could have very well been used by ancient cultures and civilizations. Mathematics is naturally encountered and incorporated as the exciting and fun tool of science that it is. Science is the window into our amazing world of nature, and mathematics is the tool to open that window. Natural physics encompasses current, futuristic, and ancient physics, and ties them together by the principles of physics that are common threads running throughout each.
Greetings, I'm LeRoy, and welcome to the Natural Physics Experience, live from Costa Rica. I have a go back to our show from last week. I stated that the power series that we encountered was our first go over from physics into mathematics. That was not quite true. Okay, here's the page we left off last week. And this drawing that I did is actually our first encounter with mathematics. This drawing represents Cartesian coordinates, the x direction, which is horizontal, and the y direction, vertical, two-dimensional space. And if you're talking 3 dimensions, then you have the z-axis. See that cross right there? That's going right down, right into the page, okay? 3 dimensions. X direction horizontal, y direction vertical, and z direction into the plane. And this is analytic geometry, which is a combination of algebra and geometry. Okay, so this schematic, this drawing that I did, that's our first encounter with mathematics, analytic geometry. And then when we got down here to the power series, that's from calculus. So that's our second encounter with mathematics. What I want to do is I want to show you the connection between these two, okay? Remember, the power series for the horizontal component of the quadrupole's magnetic field, y, which is the displacement in the vertical direction of the proton with respect to the z-axis. And then down here, you have the vertical component of the quadrupole's magnetic field, which expresses the dependence of the vertical part of the magnetic field on the horizontal position of the proton. And is why in this power series you see X, okay? All right, now, what I want you to see is these are mathematical equations, the power series for the horizontal component of the magnetic field, and then the power series for the vertical component of the magnetic field. Mathematics. I cracked a joke about this looks like Greek, right? That's an old school term meaning you don't know what language this is, right? It's mathematics, okay? It's calculus. It's analytic geometry, and we're going to get to other areas of mathematics as we continue on. But right now, all right, let's look at this. You have the power series for the horizontal component of the magnetic field that expresses that dependence on the vertical part of the proton's position. Now, because we're dealing with very small distances in the vertical direction, up or down, we can ignore this second term and on, the third, the fourth, the fifth, and this goes on, depending on how accurate you want to get. And of course, you're going to use a computer, but for our first approximation, because we can ignore the second term and on in the power series, this is called a first order derivation, okay? And because of the small distances, the small value of y, right, up or down, we can ignore all the other terms and just keep the first one, okay? And the same thing, let's go down here to the power series for the vertical component of the magnetic field. As you can see, this has x's in it, which expresses the dependency of that vertical component of the quadrupole's magnetic field on the horizontal position of the proton, okay? And once again, just like with the horizontal component of the quadrupole's magnetic field, with the vertical component of the quadrupole's magnetic field, because we're dealing with very small x's. Let's go back up to this diagram. Very small distances of x from that central z-axis. And again, in the vertical y direction, we were able to keep just the first term of the power series for the horizontal component of the magnetic field because we're dealing with very small deviations of the proton in the vertical direction with respect to the z-axis. So again, back to the vertical component of the magnetic field, because we're dealing with very small deviations of the proton in the x direction, the horizontal direction. From the z-axis, we can ignore the second, third, and on terms of that power series, okay? Because you're dealing with a very small deviation in the y direction, the vertical direction, and a very small deviation in the x direction, the horizontal direction, you only have to keep in a first order derivation, meaning the first term, you only keep the first term. And that simplifies things so you can start to get a handle on what's going on. Okay, now, the other thing I want to point out from this diagram as it's related to these two power series is that if you look in this diagram and here's the position of the proton and you have the horizontal component of the magnetic field represented and you have the vertical component of the magnetic field represented. Now remember, a quadrupole magnet consists of two dipole magnets together. Dipole magnet has a north pole and a south pole. So the two together, you have two north poles and two south poles, okay? Quite an interesting magnetic field, wouldn't you say? Okay, now I want to connect the physical quadrupole magnet and its magnetic field with the mathematics. This diagram expresses that these two power series are mathematically expressing. And there's interchangeability. There's the joining of the physics with the mathematics. These two power series that are from calculus, they wouldn't make any sense unless they said what we have seen, that for the horizontal component of the magnetic field, if the vertical displacement is 0, then the horizontal component of the magnetic field is going to be 0. And if the proton's position is such that its horizontal displacement from the z-axis is 0, if x is equal to 0, then the vertical component of the magnetic field is going to be 0, and the magnetic field is going to be all horizontal. And the reason why I wanted to really go into that is because when we go into deriving the equations of motion and the magnetic force that's involved, the horizontal and the component, and the horizontal and the vertical component of it, the fact that we've determined when the magnetic field is all horizontal and when the magnetic field is all vertical is very important in that analysis. So let's go to the next page just to give you an idea of what's ahead of us. All right. Remember, Baloundini very, very, very coolly demonstrated that force is equal to ma, mass times acceleration. Fundamental law, the second law of physics. And Osco demonstrated that one example of a force is the gravitational force. F is equal to mg. Force is equal to mass times gravity. Okay. And as I previously stated, in this case, with the particle accelerator, the force of gravity is negligible. You don't have to take it into account in your calculations, okay? The force on the scene is the magnetic force that the quadrupole is experiencing on the protons as they pass through it. Okay. Now, from experimentation, the magnetic force on a charged particle, and I know this is review. I've talked about this before in our previous show, but throwing a lot of mathematics at you, so want to review, okay? So, from physics, from experimentation, it is found that the magnetic force on a charged particle is this. It is the charge of that particle times how fast it's going, the velocity, crossed with the magnetic field. Here's our encounter with mathematics, okay? Cross here does not mean just simply multiplication. No, it does not. It's taking into account the fact that a magnetic force will interact with the charged particle at a 90-degree angle. There you see it right there. Theta is equal to 90 degrees. The angle is 90 degrees. It's a right angle. So whether you have an electron with a negative charge or a proton with a positive charge, a magnetic field is going to apply force to it at a 90-degree angle, okay, at a right angle.